This is Self-Directed Research. Our hosts, James and Amos, entertain each other with weekly hyper-focused technical deep dives. James closes out Season 2 with Intrusive lists for fun and profit. We'll take a bit of a break before starting Season 3, but make sure to like, follow, and subscribe wherever you find us to stay up to date. And visit sdr-podcast.com/episodes for all the presentations, videos, show notes, and transcripts. For your calendars, Self-Directed Research will be recording live October 9th and 10th, 2025 at Eurorust. Hope to see you in Paris or online. Finally, thank you so much to Depot, the sponsor of this entire season. Hear more about them at the end of the episode.
You have good taste, James. I'm surprised. Okay, we're going to have to do it again because I...
I'm surprised.
Of course I'm surprised.
Damn, that was a compliment until the last second stab in the back.
Nagging is a sport. Just don't do it to the people you're pursuing romantically. Just do it to your friends.
Unless they're into it.
We're not.
Bye.
Should we just cancel the recording?
Bye, Amanda. No, we got to get this one done.
I know, but how do we get our collective minds out of the gutter?
Link lists. Surprise.
So, James, what do you have for us today?
Okay, starting with a different word. We're going to go over intrusive lists for fun and profit, mostly on embedded, not entirely on embedded. All of this kind of works everywhere, but some of the things where I say it works really well are specifically on embedded. But Amos, do you remember what intrusive linked lists are?
I do. It's when the list, it's when the data is next to the point. No, there's no pointer. The pointer is part of the data, the elements. Something like that. It's good for cache locality, okay? That's what I know.
That is true. So we touched on this a little bit in What Are You Syncing About? Because we talked about intrusive linked lists being used in async await executors. We talked about it being used in things like wakers, where you want to have a bunch of things waiting on one task. But we'll do the quick concept reminder. So classic linked lists, kind of the opposite of what you said. They have separate allocations for the node, so the thing that actually gets chained into the linked list. So we're talking about doubly linked lists right now. So each node points to someone in front of them and someone behind them, or left or right, or however you want to call it.
Right.
But then each node also points to its data. So you've got this unbroken chain of nodes, and each of them point to one piece of data.
Right. And if you're a visual person, you can look at the slides that we have for this episode, because this podcast has slides. You can find them on sdr-podcast.com/episodes or on YouTube or on Spotify.
Yeah, I got to figure out. I don't think Apple has video podcasts. I think they might have like some fancy M4A format where we can embed stuff, but I haven't looked at that, and I'm probably not going to this season. Maybe that's a season 3 thing. Probably not.
Maybe it's only for premium podcasts.
Ooh, that's true.
I'm on it. Don't worry. For in between seasons, I will look into it.
Right. Whereas intrusive linked lists do something slightly different. They put a header inside of the data, so they kind of co-locate the linked list header and the data together. And so you don't have 2 allocations per thing. You just have 1 allocation of 2 things instead of 2 allocations of 1 thing, if that makes sense. The downside for the classic mode, like you said, for cache locality, you got to follow twice as many pointers. That means more cache misses. You got to do 2 allocations. Allocators take some time to do things. So the downside with the classic flavor is that you have to do 2 allocations for every node and follow twice as many pointers for every node, which is kind of a bummer. But the classic upside is that items can exist in multiple lists. So if you do have those separate, especially if you're doing something Java-y where you might want to have like a, not duplicated list of strings, and you can have multiple things pointed to them and the ref counted or something, you can maybe do this. But in intrusive linked lists, you totally can't do that. But for a lot of cases, that's not actually a problem, especially if you care about things like tasks waiting in a list instead of, hey, I want to deduplicate all of the JSON that I've received in individual strings or something like that.
Right. So with multiple nodes pointing the same data, in Java, that's easy because it's garbage collected, so it's just references, right? And the GC takes care of it. In Rust, there would be arcs or weeks or RCs, or it depends.
Something like that. Yeah, you'd want arc or ref count, or some people are trying to make GC types, but you need something to make sure that that data eventually goes away when nothing's pointing to it. And similarly, it doesn't go away until that point.
I just think they should make a Rust 2 and bring back the GC, because Rust used to have garbage collection. I love this fact so much.
Yeah, it had GC, it had actor model-y stuff. It was
green threads.
It was a squishy language for a very long time. But I've been told linked lists are bad, right? There's a whole, bunch of writings in Rust that say linked lists are bad. You should use something with more direct locality, something like a vec, because you go, hey, my processor has a cache and it loves running through linear address space. So running down a vec, even though it feels like it should be slower, a lot of times isn't actually much slower, and it makes a lot of things much, much easier. But haha, we're doing embedded systems, and it turns out that these factors sort of get flipped on their head for embedded systems because we care about slightly different things.
Oh, right.
Yeah, you can't have a cache miss if you don't have any cache. If all of your RAM in your processor is basically L1 cache, which is how most microcontrollers work, they have SRAM instead of DRAM, which means there's never far to go for your memory from the processor, which means that following a linked list is actually just as fast as a linear for loop because it's just changing the pointer and dereferencing it, which takes the same number of cycles whether you're going from here to here. Okay, I'm pointing for the audience. From here to here means very close, and from here to there means very far away. Doesn't really matter. It's still a pointer load, and so it doesn't matter.
So when's the last time desktop CPUs cared more about instruction counts than they did about cache locality? It's at least 10 years. Right?
More than 10 years, 20 years? I mean, you'd have to go back to
Are we that old?
Yeah, you'd have to go back to early 90s, late 80s maybe. It's a long time. This is one of those things that microcontrollers are running into today. So there's two main kinds of memory that we use. This is an aside that we don't need to go into, but I'll be quick. There's two main kinds of memory. There's SRAM or static RAM and DRAM or dynamic RAM. Static RAM uses way less power, but is physically larger on silicon. And so microcontrollers use just SRAM because it's lower power, and when we have little low-power devices, we want it to be there. The problem is it's physically large, so at some point, getting more SRAM closer to your processor is just physically difficult, and also it just takes up a lot of space, so your microcontrollers or your processors get much bigger. So most things for bulk memory tend to use DRAM, which is what your DDR memory is using. The problem is that uses a ton more power, but you can fit way more in a smaller package. So most desktop processors these days have a little puddle of SRAM close to the processor, and we call that L1, L2, L3 cache. And then we have a big bulk DRAM further away. And this is your main memory or your DDR3, 4, 5, LPDDR, whatever, that holds a lot of storage but is kind of further away. It's the storage unit at the end of the block rather than right in your pocket. But this is why we avoid linked lists a lot of times, because if you're jumping through hoops in linked lists and you end up having to go to that storage facility at the end of the street instead of what happens to be in your pocket, it slows you way down. Whereas if you were smart with linear operation in a vec, your processor is going to be smart and go, hey, you're running this direction in memory. Let me just go pull the whole pallet out of storage and pull the whole thing in at once. And that way, if you keep going in a linear order, we're already going to have the thing that you need. So linear iteration is great on desktop processors. But like I said, when you're made up of nothing but pockets on microcontrollers, then it doesn't cost anything to jump around. And so we get to do this for basically for free.
I like this because coding like it's 1987 or something is nice because you can beat compilers. It makes a lot of sense to write assembly, not just to take advantage of newer instruction sets and do SIMD and stuff like that. You have to be clever. There's a whole lot of stuff that we lost, a lot of art, because computers got fast enough. So I guess if you miss those days, you can just go work in embedded.
For a while, but it's starting to get to the point where we have external memory because at some point, this is one of those funny things about microcontrollers today versus 1990s desktops. The processors are about the same. If anything, microcontrollers have way faster processors these days, but microcontrollers don't have as much memory as desktop systems in the 90s had. So a desktop system like an Apple in 1990 would have probably had a 16 megahertz processor, but it probably would have had a couple megabytes of RAM. Whereas today's microcontrollers are single or dual core 100 megahertz 32-bit processors, but they still only have 500K of RAM because they don't have DRAM sitting next to them. But now we start to want it, so now ESP32s and some other ones are starting to add DRAM next to it because you want to have an 8 or a 16 megabyte buffer for audio samples or video and things like that. So in 10 years, some of this will also be a little out of date because most of the, at least the high-end microcontrollers that you'd want to run displays or audio on will have DRAM and things like that. So you start having to care about locality again, but we'll get there.
Right. And so this is what, this is just different set of constraints. And this is what -OS, optimized for size is for, or OZ even. It's for that kind of scenario, you think?
It depends. So optimization settings changes how your actual executable code is compiled. So sometimes having smaller code makes it go faster than higher optimizations because just having less to load means that it runs faster. But we're mostly talking about memory now. So for the linked list, we're talking about things in memory, and compiler optimizations mostly apply to the code size and things like that.
Wait, because the
compiler doesn't really know about cache most of the time.
The code would be in a ROM, which is different from SRAM? Like SRAM is just working memory?
Yes. But also on a microcontroller's code can sometimes be... Okay, I'll try and keep this self-contained because maybe we'll cut this because it's a whole aside. So code is stored on microcontrollers. Often it's on the chip itself in flash. So this is one of the other cool things about microcontrollers is they have all of their hard drive, CPU, and RAM in one chip. But this is also physically limiting because on-chip flash is also large, which means that fitting more into the same package means the package has to be bigger. And the problem is if you make it in the chip, then you have to sell all the different varieties because people want a cheaper one because they go, I don't need that much flash, so I want to save some money, so I want a smaller one. But then you have to ship 10 kinds of processors with different hard drive sizes because it's kind of like a MacBook. It's all soldered onto the same chip. But these days, a lot of microcontrollers, it's getting more popular to have external flash. And this has the same kind of things as like external hard drives where internal flash might only have like a slight penalty for access, and you might have cache. As long as you're accessing linearly, it goes fairly well. Versus when you have external memory, there's higher latency on that. So you can have bigger bulk storage, but it might have higher latency. So again, this is like, not only do we have cache access penalties for RAM, we also have cache access penalties for flash. And if you're doing something hard real time, a lot of times you'll just load your whole program into RAM, so you never have to pay for flash access penalties if you care about like deterministic CPU counts and things like that.
Yeah, that's what I was thinking of. Yeah.
But yeah, it all matters like this. But specifically for linked lists, we're talking about just the RAM side of things, so less about processor optimizations.
So in the world of embedded, because the physical size of the chip matters, you can't do what they do in the desktop world, which is manufacture the same chip but disable some of it for cheaper models, or like do binning and like those that are a little bit damaged, like you just disable that.
They do it too. Yeah, no, microcontrollers do that too. Okay. But I mean, there's just some limit of even in the best bin, like the physical size or the amount of power that you need to use to keep your hard drive or keep your memory online, because it costs things. Just gets too high. So even the biggest model, the best bin where everything worked, it just becomes too physically large or it increases your baseline power usage too high, and that becomes problematic either for heat or for battery life or something like that. So embedded is hard to generalize because different people care about stuff. Some embedded systems are plugged into a wall and don't care. Some embedded systems run on a tiny battery that need to run for 5 years, and so they have different optimization constraints. So it's hard to ever totally generalize for microcontrollers.
If you think shipping for desktop Linux is hard, just wait until you do embedded.
Embedded systems is fun because your application is the operating system, which means you need to know everything about your system like an operating system does. Hello, Sherlock.
This is our co-host.
And this is the trade-off, is people were like, oh, you use VEC because it has linear access order. That's great. But VEC requires alloc because you have to allocate that space. Or if it changes over time, you have to reallocate those space. And because we don't have a lot of memory to deal with, we actually usually don't have alloc at all in embedded systems. We just say, you should figure out what kind of memory you need ahead of time and don't do dynamic memory access because it can cause a lot of variability in time. Like if you have to go hunting for memory to alloc, or you tend to need more memory with dynamic memory access because you can have fragmentation and things like that. So if you need typically on average, like let's say 64K of memory allocated at any time, you probably need an allocator with a pool of 128 or 192 or something like that, because if it ever gets fragmented, you don't want to go, well, I have space, but not in one linear shot. So sorry. So it adds a lot of like variability and inconsistency and non-determinism, which we don't love so much for embedded systems. A lot of times we just don't use alloc, which means having a VEC is not really an option in embedded systems. You can do it, but a lot of times you don't. Practically you can, pragmatically you don't, if that makes sense.
Yeah, because it's... Jesus Christ. Sherlock! Now. Bah oui, faut arrêter. T'as pas vu le calendrier? But don't you have the same problem with allocations for linked lists?
Ooh, I'm excited to get there. And before we get there, one more fun fact is the Rust...
I was going to talk about this article.
Yeah, so there's an excellent book called Learning Rust with Too Many Linked Lists.
Sorry, what I call articles, other people call books. Yeah, sorry.
Your articles kind of are books.
Yeah.
But they talk about all the places where they go, you probably should never use linked lists in Rust because there's a lot of reasons. You should use vec, you should use this, you should use this. If you're coming from another language, you might reach for them, but in Rust, they happen to just not be as great as you might think because they're not abstracted away. But there's a couple caveats of like, hey, what are some cases where you still might want linked lists in Rust? And one of them is mumble kernel embedded something intrusive. And they say it's niche. You're talking about a situation where you're not even using your language's runtime. Is that not a red flag that you're doing something strange? It's also wildly unsafe, but sure, build your awesome zero allocation lists on the stack. And that's what we're going to do.
This is the best slide.
Yeah. I think this is Gankra's writing, or Aria, yeah.
In the show notes, we better have a link to that because, yeah, I believe that it's real. I recognize the frustration of maybe people trying to do that kind of stuff too early in Rust's lifetime.
Yeah.
And being like, it's a systems language, therefore it should be able to do that. And it just wasn't quite there yet. And after the 100th person asking about it, you're like, okay, you're on your own.
It's like writing any other collection, is that you can totally do it with Rust. And Rust has gotten better at making some of this unsafe stuff easier. It's just hard. It's not the first project you want to do. Even if you go, haha, I am a graybeard, I should know. You got to learn Rust, and you got to learn how to write unsafe code good. And we'll get into that, because what I'm about to show you is wildly unsafe, but it requires unsafe code, but is safe because of some of the guarantees we'll get into. So it can be done with unsafe code, but in a safe API sort of a setup.
I just also wanted to mention that when this was written, Miri probably wasn't as good as it is now.
Miri may not have existed when this was written.
Yeah, I have no idea what the timeline is there.
This might have been before the days of const, because Miri didn't exist until we had const, and const didn't exist till 130 or something. And this might predate that. It'd be good to look up. The show notes will definitely tell you whether it does or not.
Mm-hmm. Because Amanda is the best.
Yeah. So if we don't have vec, how do we do a variable quantity of things? Like in embedded systems, if you say we might have 1, 2, 3, 4, 5 of something at any given time, and this might change over time, how do we deal with that fact in embedded systems if we don't have something like vec where we can push and pop? Well, we usually use upper bound collections. So if you've used something like a stack vec before, or heapless is a very popular crate, what you do is you go, here's a chunk with room for up to 16 items. And we track what our current len is separately from our capacity, and you can push and pop things, but if you have 16 items and you go to push, it fails. And this is generally how vec itself works, but instead of failing on that 17th item, it goes, reallocates, copies over, and then goes, surprise, I had room the whole time, but actually it's doing reallocation.
That's what I was thinking.
These are just special flavors of that just never do that step.
When a vec grows, you need extra space for that to happen.
Mm-hmm.
Just like...
Yeah. And usually it'll grow some reasonable amount, like double or something like that. So if you have 16, it goes, okay, I'm going to get you 32 just so I don't have to go and, reallocate too often and things like that. But again, no allocator, not an option.
This reminds me of two things. When I was working on the itch desktop app and we started having larger games, like multi-gigabyte games, we had the problem where people had, for example, 15 gigabytes free and they wanted to install a 12 gigabyte game. And if you just download the archive and then try to extract it, that doesn't work. But I did the streaming extraction thingy where the archive is actually never stored on disk, and that worked.
Nice.
I think that's what Steam is doing too. And the other thing I was thinking about was
very cool.
When you catch an out-of-memory error, you might not have enough memory to deal with it.
Yeah. The nice thing in embedded is we usually, for all these upper bound collections, usually they're going to live in one of two places. They're either going to live in static. So a lot of times we'll just say, look, we're never going to handle more than 16 connections ever in this firmware. That's just a hard upper limit. And so we store that as a static, which means the linker actually has an option to say, do you have enough room for this or not? You can basically do your memory allocation at compile time by filling up your statics, and you tell the compiler how much total storage you have. And if you run out of storage, then it just says, nope, does not compile, you're out of space. That's great. But then sometimes we also put things on the stack, and in embedded, stack overflows are one of the most painful things to debug for exactly like what you're saying, because if I put these on the stack, especially if I try and return it or pass it up and down the stack and it makes duplicate copies and it's very large, that's problematic. But pragmatically, most embedded systems for big, chunky things, like if they're bigger than a couple bytes, or if you have a bunch of them, we're going to put them in a static. And that way there's just always space guaranteed for it. And the compiler can say it's allocated right here.
About Stack Overflows, isn't there a way, like, you have a red zone? I don't know if that's what red zones are for or something, but like...
So what a red zone is...
detect when it's about to blow. Yeah.
Yeah. So another fun aside.
This whole podcast is asides, in case you hadn't noticed, James.
Yeah.
This is our second season.
That's what we do.
Yeah, that's what we do.
So most stacks grow downwards. So when you put more stuff on there, they start at some top address and they grow downwards. Growing downwards is sort of a choice, but it's kind of like big endian, little endian. Most processors have decided that growing downward is the direction that stacks go. The way that you detect stack overflows on a desktop system is that your operating system will put what's called a red zone there. And what it'll do is it'll say, if anyone touches this, it throws a fault and we halt the program, and that's a problem. So it kind of puts like a no man's land at some limit on your stack, so that if you increment the stack pointer and start writing into that dead zone, then it throws an error, and the operating system can either choose to do something like allocate more memory or kill the program or something like that. That requires the operating system to do so and the CPU to have something that can catch that access.
Yeah, I was going to say...
usually that's an MMU's job.
That's the write barrier. Yeah, that's the MMU who would catch that, like that you're actually writing there. Because it's not like you have an interpreter or something. You can check every memory access. Well, yeah.
Yeah, exactly. So your operating system will just say, hey, this region of memory, if anyone ever writes into it, throw an error. The operating system catches that and then does something with it. So fun fact about microcontrollers, no operating systems, no MMUs. They usually sometimes have something called an MPU, which can do that protection job that we talked about, but can't do the virtual memory remapping that desktops do.
I imagine MPU for a memory protection unit?
Yep, exactly.
Okay.
But not every system has that. And not everyone likes setting that up. So on embedded systems, it's very classic that when your linker comes along and is deciding where to put things in memory, it starts at the bottom of memory and starts putting all of your global variables and your statics and stuff like that, and it places those upwards, and then your stack starts at the top of memory. So you have the largest variable possible amount, and the amount of stack memory, your max stack usage, is just the space from the top of your memory to when you hit the first variable. But the linker does nothing to set up any guard in between that, which means if you stack overflow, you just start scribbling over all your globals and statics. And when you don't have multiple threads, you only have one, so it just grows from the top downwards. That's one of those horrific programming things that everyone just accepted because that was the best you could do for a very long time, and now it's just become standard. New coming out right now processors for microcontrollers will have a CPU level stack limit where you could basically not use an MMU or an MPU and just say if the stack ever hits this number, it throws a processor fault. Because if you increment the stack pointer above some limit.
Right, you could watch the register.
Yeah. So Thumb V8, which is like the new Cortex M33, 23 processors, like the new Raspberry Pi Pico 2, have an instruction for stack limit setting. Older processors don't. And so there's a really cool tool in embedded. And the problem is with linkers, a lot of this numbers you don't really know until you're done compiling and it's placing things. There's a cool tool from Ferris called FlipLink, which does a cool trick where it compiles once, figures out what the size of the global variables are, and instead of putting them at the bottom where the stack will grow into them, it moves them to the top and puts the stack pointer just below them so that it grows downwards, because on most of these processors, when you hit the bottom of RAM and start writing into the next addresses that are not valid RAM, you do get a hard fault. You just get a processor fault that says, you tried to write to memory that doesn't exist. Sorry. And so that's a much more predictable way of making sure that your stack overflows become hard program stops versus just, hey, it happens to keep going except for you just zeroed all of your executor state tracking variables.
Yep.
Oops. And so anytime anyone comes in and they're like, hey, this is weird, it only crashes sometimes, or it does crash in debug mode, but it doesn't crash in release mode, we go, you should try FlipLink because you probably have a stack overflow. Anytime anyone just goes spooky things are happening, because that's really weird in Rust. We don't run into that. Almost always, it's just you had a stack overflow and you accidentally did undefined behavior to all of your global variables.
So you're saying Rust isn't safe?
Environments are not safe. Okay, no, we're moving on.
If you file open devmem and you write to it.
Yeah, exactly. These are one of those things that the programming language has certain rules that your environment has to upkeep, and that At some point, the language just has to say, I have to assume these facts are always true.
Yeah.
And if you violate those as the implementer, usually that's like a problem with your operating system integration. But embedded systems, everyone is writing their own operating system, basically. So if you violate systemic rules, then you have systemic problems. But yeah. To avoid this, we usually put these things in static so we can see that they are there and then track them and go, hey, it's really clear we have a baseline memory usage of this much. The downside is you have to sort of guess. And if you guess too high, you have potential waste. If you say, hey, I'm just going to say I have room for 16 connections, but in practice you only ever have 3, you're just wasting whatever 13/16 of that chunk of collection is because you just never use it. And so that memory could be used for something else or more stack, so you don't run into stack overflows as much. You kind of have to manually size these things. Too small, and you run into errors where it says, no, we couldn't allocate another socket or something like that. Too high, and you just are burning memory, which we've talked about is like one of your most valuable and not abundant resources on embedded systems. And the other side is when you're writing a library and every user wants to use a different number of sockets or connections, we put a const generic on it. So you say this is a pool of sockets that is generic over some number that lets you say it could be 4, it could be 16, it could be 32. And generics are infectious. When you have to deal with generics on multiple things, or you are making like a bigger data structure that contains a bunch of variably sized things, you can end up with like 5 or 10 generics on one structure that are just like the dials for what are the maximum sizes for these. And it's tremendously tedious to write that, and it looks super ugly everywhere you use it and name that type. And aliases can help, but it does not bring joy.
Yeah, I think the one of the most generics heavy code base that I encountered early on was Tower and Hyper with all the service abstraction. I wrote about it actually back in the days. And the nice thing on desktop is that you can eventually just do what Axum does and just box it if it becomes out of control.
Like boxed in or whatever.
Yeah, which I assume is not an option here on embedded.
It is. It's a pain. I mean, boxing is not an option. We still have like din trait. You can still do din trait. The downside is like, where do you put it? Because if you can't box it, where does it go? And you can have these kind of like stack collections or like static boxes, like one-use boxes. And we use those for a bunch of things on embedded too. It's not impossible. It's just a pain in the butt is the answer.
I see.
After all that, maybe linked lists aren't so bad, at least for embedded systems. So cool, maybe we want to try intrusive linked lists, but how? And how do we get like these linked lists where we talked about like where do we put stuff and how does it work and how do we make it safe and things like that? Like we talked about in What Are You Syncing About? We already do this in Maitake Sync because we have intrusive linked lists for wakers and things like that. So we talked about wait cell, which is just like, it's like an option waker, basically. So you have room for exactly one thing, which works really great if only one person's ever going to wait on that. But if you have 5 tasks that might want to wait on that, or in some cases 3 and in some cases 5, how do we deal with that without having a const generic for the upper bound? And the answer is intrusive linked lists. We put wakers inside of tasks, and they are pinned inside of their tasks. So they cannot be forgotten without running their destructor. And what we end up doing is we make a little linked list of all of these wakers inside of the individual tasks. So if you have 5 tasks that are waiting on something, each of the wakers lives inside of that task's memory and is chained into a single list. So that, for example, when the thing happens that all 5 are waiting on, you can go through and either wake the next one, or you can wake all of them because they are all waiting on the thing that has happened.
What is inside a waker?
It's a pointer. What is it? It's a
vtable?
Is it a vtable? I think it's a vtable and a pointer to the thing. So basically it's something.
So you're talking about the standard type from Rust?
No, well, the container is standard. The executor is responsible for providing what the contents of a waker is. So the raw waker is something that has a bunch of vtable functions and a base pointer in it. The contract in Rust is basically in that context struct that gets passed to futures when they're polled. The executor has a way of getting a waker that is relevant for the executor you're running on, but it's kind of a blind interface. So every executor defines its own waker. So an embassy waker and a Tokyo waker are not the same, but they have the same like opaque contract, if that makes sense.
Mm-hmm.
Yeah, and the waker is basically like a callback that takes a task and moves it into the ready state for the executor. So it tells the executor, hey, this task of yours is ready. Whenever you get a chance, go check on him.
You mentioned that it can't be dropped without its destructor being run, but
Mm-hmm.
What about memforget?
That's the whole You wrote pin in suffering. So the whole point of pin is that it is impossible to forget something without running the destructor of it. So pin makes sure that something is stable and in place, and it means that you can't forget it because you never have ownership of it again. So in most cases, you either box pin it, which only gives you a mute ref, which means you can't run forget on it, or it would be leaked. So it will exist forever without destructor running, and that's fine. But for stackful pinning, like when you call the pin macro, it rebinds the same name and basically hides the item from you. So you can't call memforget because you need to have the owned thing to call memforget. So you can memforget the reference to it, but that still allows the original item, which is now like has a nameless existence, to still run the destructor at the end of scope.
Sure, I know I wrote about it, James. It was a while ago, so you're right to remind me. But there's no mention of forget in either my piece or the official documentation for pin. This is why, like, the whole point of pin is something I hadn't heard before. So that's why I'm surprised.
Interesting.
Yeah.
Yeah. I mean, it's not the whole point. It is one of the major points of pin. Pin does two things. It makes sure that the item can't be moved, and it makes sure the item can't be forgotten, as I understand it, the two main things. I think the docs for pin even talk about intrusive stackful linked lists. I should have put a screenshot in here too, but I think the docs for pin actually has like, what can you do with pin? You can use intrusive linked lists because it lets you do this. And yes, it's very spooky, but these are the kind of guarantees that you can expect with pin. So when we have our list of wakers...
Fact check, they do not talk about intrusive linked lists. They talk about no STD context where you don't have access to the standard library or allocation in general.
I'd have to look. It might be at the pin module level instead of the pin type level. I think someone wrote that. I'd have to go find it.
You are correct. I was wrong. In STD pin, the module itself, it's talking about self-referential types and intrusive data structures.
Yeah, I talked to Boats about it because, Boats was interesting because it's exactly the kind of thing you can do with pin.
Yeah.
Yeah, so we have all of these tasks, and we go, where do these wakers live? They live in the tasks wherever they exist because we know that the future that the task is running is pinned, and so we can pin items inside of that task, and they exist until they don't. And then if we cancel the task and the future falls out of scope, we run the destructor, and when we run the destructor, we remove the item from the list. So even though we have this list, we know that anything that on the list is valid, because if it wasn't valid, we would have removed it. And anyone who is on the list must exist because to create something to attach it to the list, it had to exist at that point. And we know that if it still exists there, then it hasn't become invalid at any point. So we're safe to assume that no matter how spooky following all these pointers is, it must be valid because we can rely on pin as long as no one's done any unsafe incorrectly. In safe Rust, it's safe to assume these things. And similarly, if we drop the whole wait queue, the job of dropping the wait queue means running down the list and removing everyone from the list. And this is why it has to be a doubly linked list and not a singly linked list, because every node has to be able to remove itself. So it has to be able to, like, if it decides I'm going to drop myself, I have to grab my two buddies to the left and right of me, tie them back together, and then drop myself out. Otherwise, we could do some really cool lock-free programming. But since the nodes have to be able to remove themselves from the list, and we don't want to change their order, it has to be a doubly linked list.
Well, do you need to maintain the structure of the list? Like, could you just not care about all the pointers? You just navigate it in one direction and then free everything?
Hard maybe. You'd have to go ask Vyukov about that.
Okay.
So Vyukov is the person who writes a lot of those like lock-free data structures. The answer is maybe. There are cases where you can use it.
It wouldn't be unwind safe anymore. If you panic in the middle of that, you're in a very bad place. So maybe that's the reason.
Yeah. Unwind safe and panic safety as a whole. Yeah, that's a topic for another chat.
Another podcast, really.
Pin guarantees we can't skip the drop. If we drop, we remove ourselves or we remove the whole list, great. Then it doesn't really matter that these things, they don't have lifetimes that we can super explain to the borrow checker. But as unsafe programmers, we say it exists as long as it exists. And then that's the fulfilling of the unsafe guarantees there. That's our like safety comment, is we know it's load bearing. But I made a crate for this called PinList. Very unimaginatively named because it takes pinned items and puts them in a linked list. The way it works is you usually have your list in some kind of static. This becomes your like anchor point. You have a global static in your project that says this is the list where a variable list of items will go. You go, it lives right here. It's a big flag in the sand for everyone to go find it. And then every time you have something you want to add to that list, that could live inside of a task, or even it could live inside of the stack. And you say, I'm going to make a node right here, and it has a header with my linked list pointers and whatever data that I want. And all the data is the same kind across the array. And we're going to chain it onto this list. So when I want to push something onto this list, I go to the list, I chain it onto this, and I create my node item. So what I do is I pin it in place first. Then after it's pinned, you can attach the pinned item onto the list. And then it exists on that list until either someone removes it or it removes itself by dropping the item. This is really, really neat because it means that tasks can lend their ephemeral data to the list. So if you say this is a socket that holds whatever, and I need one here, depending on how many tasks you have, you don't need to go and fudge this number of what's the perfect min-max number or whatever. Anywhere you create one, it exists. And you don't necessarily need to worry about them because if they exist at different stages of the tasks and things like that, you always know there's enough room because if it exists in the task, there must be storage for it. Therefore, if it exists in the list, it's good to use. But wait, I just said I'm going to put something in a static and then I'm going to point to non-static data from that static. And that's like Rust's whole thing, that you're really not supposed to be able to do that because you're taking items that have a lifetime that does not live as long as static, and you're storing them in a static and then calling that static lifetime. How do we do that? And the answer is it's unsafe. Like, we use unsafe code to do that. But we can put a safe exterior on interiorly unsafe code because that's how all abstractions in Rust work is you limit the blast radius and then you put a safe outer shell on it. And then you say anyone who uses this in safe code never has to worry about unsafety because I've done all the spooky stuff inside. The trick here that I didn't really mention is that you can only access the items on the list while you're holding a blocking mutex. Not an async mutex, a blocking mutex. And what this means is that when you add stuff or remove stuff, you have to hold the mutex so you can access the list and add or remove something from it. Or if you want to run down all the items, like I want to iterate over all my sockets, you need to be holding a mutex for the whole time that you are running across that list. Because the mutex acts not only as mediating exclusive access, so like being able to do mutable things to each item on the list, it's also preventing you from adding or dropping anything to that list. So an item can't drop itself off the list if the mutex is already being held.
Yeah, I was going to ask, well, what's preventing you from doing that? Does it just not throw, but panic? Like, how does it check? Does it block indefinitely?
Well, it's just a blocking mutex. So if you try and get the mutex in your destructor, it's just going to block until it's able to get that mutex. So if someone's iterating over it, you have to wait until they're done iterating. They release the mutex, then the destructor can grab the mutex, remove itself, and go on. But the code just blocks if you try and do this.
Yeah, but is there any provision against deadlocks?
Yep.
So the way you access mutex, like I'm looking at the API right now, and there's a with lock method on node handle, and it takes a closure and an FN once. What if you drop another node handle in there? Then you have a deadlock, right?
You would, if you're accessing it from the node itself. Let me go back to the picture. If you're accessing it from the node itself, you typically in your local scope only have access to your own node because you've declared it there. The only thing you have in other scopes, or your only way of seeing other nodes, is through the PinList method that gives you access to the other items. I think, yes, you probably could make it deadlock in some way if you I will make two nodes here that I have local context to, and while I'm holding the mutex, I will try and drop the node. But actually with pinning, it's very difficult to manually drop something because you don't have access to the original item. So the only way to really make things trigger drop is to make them fall out of scope.
Yeah.
And to make them fall out of scope, you have to return. And if you're inside a scope where you're doing this stuff, you can't really return from the scope while you're doing something else, if that makes sense.
Yeah.
So you probably could, in a very convoluted way, shoot yourself in the foot and cause it to deadlock. It's not particularly easy to do with the interfaces I've given you here.
Well, I guess the easy case is just two nested calls of with lock, but then it's pretty visible, like within passcode review.
Yeah. You'd be in a blocking context and you'd be calling lock to get access to the thing you already have access to. So it would, you probably could deadlock, and at that point, like a stood mutex, if you try and lock it while it's locked, it'll deadlock if you're in the same thread. If you're in a different thread, it will just block.
Yeah.
If you're in the same thread, it will just deadlock because it'll detect that. On embedded systems, we don't have the operating system locks.
So when are you adding a deadlock detector Just like, what's the...
The answer is I kind of actually do, because on desktop, if you're in the same thread and you lock it again and it would deadlock, stood mutex will already panic. On embedded systems, we don't have stood mutex, but I have a crate called mutex, and it uses what's called a scoped blocking mutex. On embedded systems, to handle this, we're gonna take like a critical section or whatever, and if you go to lock it again, we will see that it's already locked, and so we can do the same deadlock detection where it'll just panic. So if you deadlock, it will panic, but the answer is it's exceedingly hard to deadlock unless you're trying, I would say.
All right. Well, good thing deadlock detection is super easy on with a single thread.
Yeah, and running drop means holding the mutex. So actually running the destructor here means that if you're not holding the mutex, you have to wait. And if you're holding the mutex so you can drop, you know that there are no other live views of the list, which means there's no problem because no one can have like an item spookily pulled from under them. And the interface for gaining access to this doesn't let you return a reference to an item on the list outside of the closure of holding the lock, which means you can never like return an item beyond the actual call, which means all your access of the items has to be done with the mutex locked. You can't just hold on to a reference that could get stale because someone could decide to drop it, which means you do all of your actions immediately rather than holding on to something and doing it later.
This feels weird because there's pin, so I would expect async, but no, it's all blocking, it's all synchronous.
Yeah, it's correct. Yeah, pin is not exclusive to async, and we do need to do it blocking because there's no async drop right now. So once we get async drop, I could probably loosen this restriction and be able to do async drop here, where something can yield until it's able to remove the item from the list. You'd still only be able to do it with it held. I do actually have another variant of this. Well, I'll mention at the end. If you make all of your items static instead of pinned, so that they can never be dropped, you actually can use an async mutex to this and not worry about it, because then you know items are always live because they are static items and they can never be dropped. And I actually use that in one of the libraries I'm going to mention because we do want async for some things like this. But you actually can...
But then why do you need a linked list if it's only static items? Like it's just to maintain an order?
I'll get to it in a second.
Sure.
Back to talking about holding non-static things in a static item, it's good enough because we know that as long as it's on the list, it lives long enough. And really, static doesn't mean lives forever. It means how old are you, old enough to drink kind of thing. Like, it's like, that's probably a joke metaphor that's not going to make a lot of sense.
No.
So the answer is, it just needs to exist as long as anyone could possibly want it. Sometimes that means forever. Sometimes that just means long enough. And so that's what we're doing here. Everything lives long enough because it lives as long as it's on the list, and if it's not alive, then it's not on the list.
Static is sometimes code for just owned. Like, I think if it is owned or like self-contained or something, like it's not borrowed from somewhere else. So we control its lifetime.
I really think of it as lives long enough, because if it's owned, it always lives long enough because it lives as long as you hold it. And if it's in a static and lives forever, obviously it lives enough because it lives forever, and forever is always long enough. You're right. There's like in-between cases between owned and like a static forever reference where it really does mean it lives as long as it could ever need to. So that's usually how I think of tick static, is just it lives as long as it could possibly ever need to. And that means for as long as someone knows about it, it exists. And for owned things, only one person can know about it, or as long as the borrow lasts and things like that. So yeah, I think a good way to think of static is it lives as long enough as someone could possibly want it to. So the reason why you might want something like this, both in the like the pin case and in the like everything's a static case where it's a variable item, it lets you do a very cool thing of separating ownership of resources from a worker of those resources. So what I mean by that is because you have this flag in the sand where everyone can meet, either to add items to the list or to access the list, you can have your IO worker task independent from all the items that are storing things, which means you can do cool things with different libraries. So one library that I've written is called config noodle. It was a silly placeholder name.
Love that.
This is one of those things, I have a habit of adding placeholder names. This was originally written because I was just noodling around. I was trying to figure out what to do before it. So like on a guitar, when you're noodling around, it's just like improv and not really doing anything meaningful. So I named the repo config noodle because I was just noodling around to figure out what I wanted to do. And then the customer never came up with a better name. And so now the library is just released as config noodle. But it does things where it holds storage. Like you can have a config item that exists in all the tasks. And then because that storage in the config exists on external storage, you have one IO worker task that just whenever any of the config node says, I would like to store data, or at the beginning at boot up, they go, I need to be hydrated with my data, they can just raise a flag, and the IO worker, which is totally separate, can just access the external memory, populate all the items on the list, or grab the items on the list and flush them back to external memory. So instead of everyone having to hold like a reference to things where the generics have to be consistent because all the items have to be of the same type or whatever, you can just say, okay, IO worker lives over here, and then all the nodes live over here, and they just exist in the linked list. And by having a node that exists in the linked list, you get the benefit of someone running the IO task for you. And your IO task is totally independent, where it doesn't have to have references to however many tasks you have. It just says, I just run down the list whenever someone asks me to, and I either flush data to the disk or I load data from the disk. And it works really well. And this way you can basically have storage for keeping all the items cached wherever they are. So anywhere where you have the item and you would like to have access to it, that's where your cache exists. So you don't need to figure out exactly how much cache I need. You just have the right size of cache everywhere where you have an item, and it just exists inside of the task. So it's always right sized. You don't have to like tune any values to figure out how much you need.
That is really cool.
Yeah. This is like a very classic way of doing things on embedded systems or kernels. Like, it's just not usual that you have a safe interface to it because the language is expressive enough to like not totally make the guarantees. You still have to write the unsafe under the hood, but it can at least express that on the exterior so you can use it safely, if that makes sense.
Yeah, you don't have to write any unsafe code to use PinList, right?
Correct. Yeah, I've written all the unsafe for you, so as long as you just use it with its public API, it'll always work, and you won't have to write any of your own unsafe code.
Yeah, that reminds me of the Rust in Linux work, where they made safe interfaces for a bunch of stuff, and a bunch of people were like, oh, this looks complicated. I'll do that one again.
Turns out this was everything that you had to do anyway and was just implicit.
Yeah, exactly. And like now we're just annotating that, and this can never go wrong because of that.
Yeah, we can describe the contract in the way that the compiler can enforce, even though we can't describe what's going on under the hood in a way that the compiler can understand because there's pointers and whatever. Yeah. We can at least explain the contract in a way that the compiler can enforce, which is super useful because the person who knows the most about this is the implementer, and most of the time the people who know the least about it are the users of it. And so you want to like protect all of your users as long as one maintainer understands it and can rely on the compiler enforcing that rule.
That's one of my favorite things to explain about Rust, especially when people are frustrated about it. It's that the number of programs that the Rust compiler will accept is very small compared to the number of programs that are memory safe. But that's the compromise we make because all the programs that are accepted are safe. So you don't have to worry about it.
Exactly. And the other place that I'm using this is in ergot, which is my networking or message communication library for embedded systems, where all of my sockets work basically the same way. The sockets are things that you hold in the tasks that you're using them from. And there's IO worker tasks where if you have an external interface and a packet comes in, it can run through that list, find the destination for that packet, and drop it in the correct socket. Or it can run to the end and say, I didn't find anyone, send a negative acknowledgement back or like a knack and things like that. And that way, it doesn't matter how many sockets you have, or if you go, oh, I only have this socket open in this mode, or, you know, I only want to open a socket just long enough to send a request, get my response, and then immediately drop my response because I'm only waiting on one response here. So you can have ephemeral sockets or sockets that live forever or as many as you want and things like that. And the IO worker task that's taking these incoming packets just goes, hey, look at the header, figure out the destination. Is that here? Do we have a socket like this? Yes, we do. Drop it in and then move on. And because any socket can then just send directly in the outgoing queue, it means that now you don't have to tightly coordinate in all of these things, and you get the same kind of feeling interface that an operating system socket library gives you, but it's all in user space. Like, it's all just linked together in a way that keeps this reasonable, that as like a firmware developer, you get something that feels like something an operating system would give you, but is actually totally done in firmware. There's a little bit of code behind the library, but there's no magic behind the operating system because there is no operating system. Like I said, it's a pretty handy pattern, and it's how I've been building a bunch of libraries. This is like a streak that I've been on, is I kind of went back and looked at wait queue and went, I wish we had that for more general stuff because I could use that for a bunch of stuff. And then I started using it in ergot, then I started using it in config noodle, and then eventually someone was talking to me about it and was like, hey, how would I do this? And I go, you should use this pattern. Here's a link to like 500 lines of unsafe code. Just do what I do and also hold it right. And I went, well, that's not great. So I eventually extracted PinList. PinList only does one of the two tricks. So both ConfigNoodle and ergot take this one step further, where PinList requires that all the items in the linked list are of the same type.
Right.
So when you iterate over them, you get the same type on the same place. But actually, ergot and ConfigNoodle, and also async executors that do this kind of stuff, don't. Every item has a common header, but then you have basically like a din object below that pointer. So on all those sockets that I talked about, they all have differently typed deserializers because they're given the message, but one socket might be of this type and one socket might be of this type. And same with configuration. One configuration element might be of this type and one configuration element might be of this type. And what you do is you actually have a vtable in all of the nodes. And so the IO worker that's coming along can go, is this for you? Yes, it is for you. Cool, I'm going to call your vtable method with like a raw pointer and just do it. So the second stage of this is actually like really spooky type erasure, which is, I think someone actually sort of figured out how to get din trait working in PinList. I'd have to check and see if that PR is still working and if it's still sound. But the vibe of what ConfigNoodle and ergot are actually doing is basically having a linked list of din trait items so that you can hand them a packet and go, did you like that? And then they have at least a consistent interface to say, yes, I did, and I took that message. Or, no, I didn't. I don't want this. And that way the IO worker, that's all the IO worker needs to know. They don't need to know what it did with it. They just wanted to know, did I deliver it to you or not? So that's the spooky second half. That's a whole nother episode. But just storing items is a pretty neat technique. And then you can take that neat technique a little further at some point if you want.
So with items of different sizes, you still need some sort of dynamic memory allocation, sort of.
You do not.
You don't?
Because they are stored inside of the task. And the task knows what type that's the trade-off, is the list doesn't know what type they are, but the nodes know what type they are. So when you create the item inside the task, it knows it's the specific item that it is, but then it just has the common header that's at the top of the item, and that exists in the list, but they can be of different sizes in every single task.
Right. This can all happen on the stack is what you're saying. Or static.
Yep. In embedded for tasks, we actually statically allocate our tasks usually. So they exist as basically like reusable boxes for specific tasks, because in Rust now we can figure out the size of a future. And if we can figure out the size of a future when we're creating the task, we can make a perfectly sized static that is the size of this specific task. And then we just say we can have 1 of those or 5 of those or 10 of those or whatever. So it's kind of magic. It is stored in a static, but it's the compiler figuring out how large that static needs to be.
Yeah.
And then you don't have to think about it, and you just know that it's bounded, like, okay, I can have up to 4 of these exist at the same time. So we are kind of doing that like fixed upper bound kind of thing, but most of it's hidden in the executor's plumbing where you don't have to care. But you are still at compile time deciding how much memory you need for all of your tasks. But the thing is, these sockets or whatever could just be one leaf future state inside of that whole task. So if you have like part of the time I have this socket open and another part of the time I have this socket open, you don't need to reserve space for 2 sockets because the compiler is smart enough to tell these 2 states of the future are never live at the same time. So I just need like kind of like an enum. I only need the superset max size, not the sum of all size, just the max of all leaf states of a future.
That reminds me of an episode where we argued a little bit about how easy it is to write async code. And I think in the comments, someone said, Amos, actually, you're wrong. Like, the tooling is good now. It's fine. So
it got better. There's still some stuff where there's rough edges. And I think both of us are on the same page of like, we know the places where it sucks.
Yeah.
And we know the places where it's actually pretty good. And we know that the set of places where it's pretty good is getting bigger over time. But there's still like a non-zero set of items that kind of sucks to debug. But yeah, it is getting better.
So how many of those libraries, those crates, are you maintaining now? How big is the dependency tree that is your own under your network stack?
The network stack, I'd have to look at the dependencies. So there's 3 libraries basically where I'm using this trick. I mean, I listed all of them. There's ergot, ConfigNoodle, and PinList.
Yeah, but it's not the only pattern, the only like idea you've turned into a crate, right? You've been publishing a bunch of those.
Of this one so far, yes, because I really only started doing this a couple months ago. But I'm sure I will have more by the time that probably anyone's listening to this. But the main 2 dependencies to make this happen are cordyceps, which we talked about in What Are You Thinking About? It's the intrusive linked list library with the best name ever. because it's named after a fungus that invades your brain and makes you do stuff. So the intrusive linked list library is called Cordyceps. That's from Eliza, and I guess I help out with that library. So it's Eliza's library, but I have made a lot of PRs to it.
Right.
And that's used also by Maitake Sync. So like WaitQ and WaitCell are using Cordyceps under the hood as well. And then all 3 crates that I named are using this for the intrusive linked list. Then for that blocking mutex, there's a crate called Mutex, which I also own with Eliza, and that's used in all 3 of those crates. Actually, no, I don't think it's used in Config Noodle because, like I said, we made them static, so we don't need a blocking mutex. We just say that every node lives forever. So it's not using that. But those are the only 2 main building blocks. And I think Cordyceps has no direct dependencies, or maybe just 1 or 2 small helpers. And the mutex library also, I think it depends on what feature you use. Like on embedded systems, you want the critical section crate. And then on desktop, it's just using std mutex, if I remember correctly. So it's not a deep dependency list.
Fact check. Cordyceps has no dependencies. It has like 3 dev dependencies and a Loom feature that enables Lumen tracing for testing, I'm assuming.
That makes sense.
Yeah.
And then the mutex crate probably is just based on like, it's generic over, you tell me how we can make a mutex, because that way on desktop you can do one thing and on embedded you can do another thing. So it probably has a couple of dependencies depending on which feature you enable, but in practice you probably are only ever enabling one of them. So it'll be like either the Cortex-M crate or critical section or std, maybe actually just critical section with the std feature enabled. So
Gotcha.
you don't really need a lot of depths to do this, because like the depth of the UNSAFE code that you need here is pretty shallow just for the data structures. And then what you do with it on top of that is sort of the question. So like Config Noodle then relies on the CBOR library, which is a serialization and deserialization library, which is how you implement those vtable methods for like loading and storing, and then some other like storage libraries for how you store stuff externally. Ergot at that point, Ergot base is where I do all of this stuff, and then Ergot's like the nicer, higher level interface over this. I'd have to look. Ergot's like 10,000 lines of code at this point, and then the depths, I don't know. I'd have to look at, I don't know exactly what my load-bearing depths are there, but there's more there because I'm doing stuff with like Postcard and Serde, and I'm using a bunch of crates from the Postcard ecosystem in there, so those probably have a bunch of recursive depths as well. But for the actual just like this pattern, you need like 2 libraries. You could totally do it yourself if you wanted, but Cordyceps is a really good library, and the Mutex library is exactly what you want for this, so probably 2 in most cases, unless you're doing additional spooky things, but then it's just whatever. Yeah.
It's just looking forward to see the James cinematic universe grow.
Yeah. We'll get to Ergot probably next season. I was thinking about doing Ergot for this last episode.
Yeah.
But I could do a season on Ergot, so.
We both decided it was too much.
Yeah. So maybe season 3 is just going to be the Ergot season at this point.
Exactly.
I think that's a good end.
This episode is sponsored by Depot, the build acceleration platform that's on a mission to make all builds near instant. If you're tired of watching your builds in GitHub Actions crawl like the modern day equivalent of paint drying, give Depot's GitHub Actions runners a try. They're up to 10x faster with unlimited concurrency, faster caching, support for Linux, macOS, and Windows, and they plug right into other Depot optimizations like accelerated container image builds and remote caching for Bazel, Turbo Repo, Gradle, and more. Depot was built by developers who were tired of wasting time waiting on builds instead of shipping. It's made for teams that want to move faster and stay focused on what actually matters. That's why companies like PostHog use Depot to cut build times from over 3 hours to just 3 minutes, saving tens of thousands of build hours every week. Start your free 7-day trial at depot.dev and let them know we sent you.